And we are going to transition to the next talk where Kurt Samuelson is going to tell us more about how we can make the large repo feel like a small one.
Hello, my name is Kurt Samuelson. I'm a Principal Group Program Manager in Microsoft Developer Services. My team builds the engineering systems that Microsoft uses to build its products. Today, I'm going to talk to you about how we balance bringing speed to the engineering process at the scale Microsoft requires, while we also focus on improving the engineering experience. For individual developers, that means providing them with the ability of working in a small repo, even though they're actually working in some of the largest repos in the world. I want to start out by giving you a sense of the scale that we're working with. There are over 27,000 active repos, meaning these are repos that have had at least one code submit in the past 90 days. There's over 800 terabytes of source code, the largest single repo being 22 terabytes. That code contains almost 10 million active OSS package references, representing 64,000 unique packages. 15,000 pull requests are submitted on average every day. 300,000 builds on average are run every day, and those consume about 900,000 compute hours between build and test every day. In addition to size, engineers deal with a lot of complexity in their work. We find that a single engineer often needs to work across more than one version of an SDK or other tooling, depending on which branch of the code that they're working in. This is also true for OSS packages and many other tools, creating a complex environment that often makes it difficult to utilize the benefits of desktop tooling and the IDE of their choice. We're a large company. Teams take dependencies on deliverables and features from other teams. This adds complexity. We work across different industries that require our compliance to certain policies and standards throughout the engineering lifecycle. Oftentimes, these compliance boundaries overlap, creating redundant and possibly conflicting guidance. Then there is our own corporate policy around things like privacy and security that need to be followed throughout the development process. All of this means that there's a lot of complexity that engineers end up dealing with. And engineers have told us that sometimes they feel like they're fighting with the engineering system, or at least they have to do extra work to use it. For them, this means that it can take 40 minutes sometimes for an engineer to start up each day. They clone a large repo, they load that code into the IDE, they search through the code to find the area they need to work on, they manage a set of solution files in Visual Studio, and they run a clean build to seed their local cache. Oftentimes, engineers have found that some of the optimizations that we've done to help speed up outer loop processes can, in fact, sometimes slow down their local desktop builds, further complicating their life and the processes that they do when they build their software. It's also the case that pull requests can sometimes fail for no reason at all. This can be caused by infrastructure failures, by differences in build configuration between local machines and pull request agents, and by flaky tests that sometimes succeed and sometimes fail with the same input. Clearly not a great experience for engineers. And we get feedback that they often feel that they are manually holding the system together as they work. At the end of the day, engineers tell us that they just want to write code. This is what makes them happy. And in fact, we see this as a correlation in the satisfaction surveys that we do. The amount of time spent coding is highly correlated to their satisfaction and their happiness at the company. However, the reality is, on average, engineers only spend about 1 hour a day actively working on code. So, how do we approach the problem? Our engineering system approach is anchored on a pyramid model. At the base of this pyramid are the Microsoft retail developer products: GitHub, Visual Studio, VS Code, Azure DevOps, Azure. We want most of the capabilities and the experience for engineers to be delivered from this foundation. This benefits the most people, both inside and outside of the company. The middle layer is the core engineering system, sometimes called the 1ES engineering system platform for the company, that integrates the retail products into end-to-end experiences for engineers that drive productivity and satisfaction for them, and provides the scale, performance, compliance, and security that Microsoft requires to run its business. At the top of the pyramid are the individual product and service teams. There are often unique aspects to products that require customizations to engineering systems. Our federated model for this last mile enables the company to scale out to meet these requirements. Boundaries between these layers are fluid. The core engineering system delivers features into the retail product in addition to building custom solutions specifically for Microsoft. And individual product teams incubate local solutions and can contribute those patterns back to the core engineering system or to the retail developer products themselves as well. With that backdrop, I want to talk through how we address the problems that I outlined earlier. We started by addressing build and test performance. There were large official build processes at the company that could take days to complete. This meant that the customer feedback cycle was very long, and we worked to move these teams to a parallel and distributed build environment. A key challenge was that in moving some of these products was the amount of build collateral that they had built up over the years. It would be a non-starter for us to come up with a great acceleration story that required teams to rewrite this build logic accumulated over decades, or to require them to rewrite test collateral, for instance, to a new test framework. So a fundamental design goal was to meet the teams where they were with their existing test and build collateral, as we delivered a highly parallelized build and test infrastructure to them that enabled builds to complete in the time the longest some process runs. For instance, the longest running single test should be roughly the length of a complete test run. For the largest repos, official builds went from days to hours. This is a very big deal. It enabled teams to get code out to customers several times a day instead of a couple times a week. Despite all the goodness that happened in terms of speeding up official builds from days to hours, sometimes engineers' local desktops builds were not improved, or they even degraded. So why did this happen? To accelerate a build, we first need to build something called the build graph. The build graph looks at the build, determines what needs to get built in what order and in the most optimal way before it distributes that build out to the cloud. This graph generation can take time, 10 minutes, for instance, on a large repo. This is fine when you're optimizing from a build from days to hours. However, it's not so good when you just need to build one file and check that back into the repo. So we needed to extend our caching and build acceleration technology beyond official and pull request builds to enable that to work with desktop builds as well. The next area we focused on was simplifying the security and compliance landscape for developers by shifting security and compliance to be addressed earlier in the development cycle, or shifting left. This reduces the cost of compliance and security by addressing the issues before they are in production. In particular, we are focused on addressing security and policy at coding time. Some examples here. Code is scanned for credentials on every push. If creds are found in the code, the push fails. OSS components are checked for unlicensed usage and for known vulnerabilities at every PR. Finding either will fail that pull request. Policies are applied throughout the lifecycle with automated policy gates that will stop the pull request or a deployment if it's non-compliant. Hashes of build artifacts and process attestations are logged into a software bill of materials that provide provenance and process verification. And finally, build processes run with low privileges. So should the engineering system be compromised, the blast radius is limited. A next area of focus was around managing repo health. We call it gardening in the sense that repos need tending and maintenance over time to perform well. Tools get updated, but builds often rely on specific versions of tools. So we check those tools and the configuration into the repo. This created a new set of problems in that Visual Studio would typically upgrade MS Build, SDKs, and compilers alongside the Visual Studio IDE upgrade, meaning that engineers could not upgrade to a new IDE until the repo updated its toolings. So decoupling the IDE upgrade from tool upgrade was a critical step in enabling us to keep the repos healthy and engineers on the latest version of the IDE. We then created a tool to centrally submit and manage pull requests to repo owners with updates to compilers, SDKs, and other tools, enabling us to keep the 25,000 repos at the company up to date over time and at scale. We had made good progress on the fundamentals, improving speed, security, compliance tooling, and repo health. Engineers were still not happy with the engineering system. So we needed to understand why that was, what the experience engineers were having with the engineering system. And the best way to understand that experience is to instrument and measure it. This enabled us to benchmark teams, repos, products for things like pull request velocity, average build times, where there was dead time in teams' processes that could be automated and addressed through automation or other cultural changes. Because we know what tools were running in a specific repo and what experience the repo looked like through telemetry, we also provide repo owners with recommendation on what changes they can make to improve the performance and experience in their repo. We as the central team can also look across the company for opportunities to standardize best practices and tooling. The final big area of investment was integrating the pull request experience and the desktop experience for engineers. A primary goal here to enable the developers to live in their IDE, be that Visual Studio or VS Code, and not have to context switch between command line tooling and the editor, and limiting the need to remember arcane knowledge of how the engineering system actually works. We improved code search capabilities in the IDE. We provided an ability to do solution filtering inside of large repos so that developers can work on portions of the code in the context of a very large repo much easier. We enabled sharing of the build and test artifacts between official builds, pull request builds, and desktop builds, and provided acceleration on the desktops to give engineers the confidence that what they're building on their local desktop will match what is being built at PR time. So what does this look like when we put it all together? I'll walk through a few key extensions we built and then show how we work together. They work together as a cohesive engineering system. Our build acceleration infrastructure starts with the fundamental design goal to enable any build agent, be that an official build, a pull request, a buddy build, or a build on a developer's personal machine, to utilize the same caching and compute capabilities. So build agents from GitHub Actions, from Azure Pipelines, or from a developer's IDE can initiate a build that has access to shared caching, artifacts, and compute resources that the official build process uses for the repo. Build definition and tools on on the build client are reflected to the build cluster, so no custom build logic or scripts are required. The build cache is also shared across build clusters and tenants, so we can optimize for building dependencies across repos. This supports building on Windows and Linux, and local builds are optimized to use the compute from the local machine as well as the cloud resources. This approach has sped up all builds, gives developers confidence that what they build locally will build in the same way that pull requests and official builds are built. For the test infrastructure, the primary directive was to be able to use existing test collateral and frameworks while we parallelize test execution. The system has three main components: a control plane. This consists of resource management, image management, test session, and execution management, and an API to enable teams to integrate with local tooling. The data plane is where the tests actually get executed. We support this for Windows and for Linux, or the tests can also be called out to a custom resource provider for specific hardware or operating system support from on-premise labs. The data plane manages key test scenarios like multi-machine testing, reboots, holding VMs for debugging, and before they're recycled back into the pool. Flaky test management identifies tests that fail non-deterministically, meaning that given the same input, the test produces different results at different times. These features enable teams to quarantine these tests, automatically create and assign bugs for them, and configure retry logic to reduce the pull request failure rate due to these flaky tests. Test jobs are kicked off by a GitHub action, Azure DevOps pipeline command. They take data from Azure artifacts and test cases from the source repo. Test cases are output to Azure test plans. Of course, telemetry is captured, and that is fed back into the flaky test management component, where bugs can be filed in Azure boards. For telemetry, our objective is to understand the performance of the overall engineering system and the experience engineers have with it individually and as groups. To do this, we pull data from Azure DevOps, from GitHub, from custom tooling, and other enterprise data sources like SAP that provide organizational hierarchy data. So we're able to coordinate the engineering system telemetry by team, by repo, by product, or by other relevant dimensions. The data is schematized and processed into an Azure Data Lake storage account, which can be directly accessed or accessed via Azure Data Explorer. Putting these systems together, I just talked about with the MS Retail product offerings, we land on an ecosystem that looks like this. The developers at the center. They interact with the source code and submit pull requests through a desktop experience in IDE. Pull request automation is managed via GitHub Actions or Azure Pipelines. Those in turn are governed by a policy automation and enforcement system that ensures OSS packages are scanned for vulnerabilities and proper compliance. The appropriate static analysis tools are run against the code. And it can inject policy into build, test, and release management tasks that can gate progress through the deployment and pull requests. Throughout the process, attestations are collected about the engineering process. The provenance of build source materials are used to create software bill of materials and stored for audit and compliance. Build and test artifacts are cached and stored in Azure Artifact Services, and telemetry across the ecosystem is collected for reporting and analysis. We're not done yet. We continue to learn from our engineering community through telemetry and surveys. We're continually updating support for new tools and technology in the development environment. with an end goal of delivering a secure, compliant, and satisfying experience that largely stays out of the engineer's way.
Awesome. Thank you so much, Kurt. It's been a fascinating story. I really admire the amount of engineering that went into designing such well-defined layers for each of the piece of infrastructure that you use. We are a bit behind the schedule, so I'm not going to ask many questions, since hopefully we're going to have you for the panel, because I do want to talk about the standardization of the efforts. But what I wanted to quickly ask is so for example, you mentioned the component for detecting flakiness of tests. And this is not necessarily just an issue with tests. It's actually just with any type of signal, there could be some sort of flakiness like this. The same thing with build, for example, especially in a distributed build, when you produce some parts of the binary, they may not be necessarily deterministic, so you can essentially treat them as flakiness and whatnot. So I wonder if you have any ideas or thoughts or plans to build a generic infrastructure for just signal quality assessment, where test is just one type of signal, but there could be many others, and then a lot of the principles for deciding whether it's high quality or not could be shared. So do you have something like that?
So I think the challenge is domain knowledge around what is good signal quality and not out of these systems. So from a test perspective, we spent a lot of time with test engineers and the data that we had to say, look, how are we going to actually tune this so that the signal to noise ratio is actually the right thing, that you can act on it. If we're going to get this signal back and we're going to tell you that this is faulty and we're going to file a bug on you or your team on this, typically they want to know that this is a good signal, right? Otherwise, we're going to be filing lots of bugs against someone and it's going to look like noise and people are going to ignore that, and then those flaky tests are going to go back. So in general, I think that your point is right, is that there's lots of applications for looking at and understanding what is a deterministic outcome. Is there flakiness in understanding whether this signal is good and I can trust that? There is always some nuance around this in terms of the specific domain that you're looking at.
Yeah, and so the other thing is that I had in mind is, so since you have such a cohesive system, it's not just part of a bunch, like some hacked up components that happen to work together. I wonder if you have some sort of backpropagation system where you trace all the systems from code initiation to the deployment, and then feed it back to inform the signal providers about the quality. So for example, let's say you have tests that may fail, but in production, it doesn't have any impact. Or maybe you have some sort of linter warnings that you treat as warnings, but they actually in production seem to correlate highly with, let's say, performance regressions or some sort of crashes. So this way, if you have, let's say, a signal about, I don't know, potential memory leak, let's say, and then in production you detect an actual memory leak, you can inform the signal provider about the one that was complaining about the potential leak, that it was actually indeed a leak, and we can boost the signal value next time we run it. Do you have something like that?
So I'll say our focus on flaky tests specifically is a much less sophisticated approach than that, and it actually got us quite far in terms of taking this course approach. It was simply to identify when tests that were run with the same input consistently provided a different level or a different outcome or a success rate with that. And simply by doing that, we were able to up the PR success rate by about 90%. So the thing that you're talking about, I can see that there's probably some benefit to that. I would recommend, if you're specifically looking at flaky test. And in this case, oftentimes things that are identified here are, poor logic in the test in terms of managing timeouts from other services, as an example, right? So that's why it failed. Well, what are you going to do to improve that test to make sure that that test can actually handle that timeout properly and not fail and pass through properly as part of that? The question of how do you triangulate back to the actual source is that we've brought that context up in the notion of test selection more than in the context of flaky tests, meaning that how can I optimize the tests that I actually do want to run at any one time so that I don't have to run all the tests at once, but also having confidence that if it fails sometime throughout the day that I can triangulate back and find out where that failure was, and then reintroduce and roll back to that point. And so we think of that as a test selection problem more so than a test flakiness problem.
Yeah, that makes perfect sense. It's just actually, I'm just saying that essentially what I'm talking about is the generalization of this technique. Because first of all, you can the question about efficiency and how much time you can spend at diff time, let's say, or len time, in terms of resources, in terms of time, is very important, because obviously it would be great if you could just run all the things all the time, but it's just not scalable. It's
That's
like
right.
It's fundamentally going to take a huge amount of resources and potentially going to have a very, very poor reliability, just because there is always a chance that something's going to go wrong. Even if you have a very, very resilient infrastructure, if you have so many things, then just by virtue of probability, you're going to have some issues. But anyway, sorry, since we are out of time, I would like to continue on the standardization on the panel discussion. So thank you so much. I'll see you hopefully in an hour or so.